It's my pleasure to introduce Maryam, who is probably one of the most productive people in our department. She is currently the she occupies the Asha Nawani chair, and Maryam did her MS and PhD from Sharif University of Technology in Tehran, Iran. And she worked for a couple of years before she joined our department in 2001. And then we did not allow her to leave. She has written close to about 350 papers, has 45 Indian patents and 6 US patents. And she was awarded the Qualcomm India Faculty Award in 2021. She was the distinguished lecturer of IEEE sensors from 2022 to 2024, I think. And currently she is also the distinguished lecturer for IEEE Women's Chair, I think. She has got, of course, a very large number of awards, and H.H. Mathur is now one more added to the long list. Please, Maryam, let's hear about analog mixed signal.
Thank you, Professor Harish. It's my pleasure to be here among all of you and then briefly explain about some of the research which has been going on over the last 10 years. And it's an honor to have this award from IRCC, and then thanks to Dean and Associate Dean, as well as Head of Department. On Monday also I said that really they play a very important, vital role in enabling all of us to actually do the research. So I actually work in these 3 underlying boards, and the main reason is because they are connected very well to each other. In today's world, when many things are based on sensing, specifically when we talk about the automation and when we talk about the how to make everything smarter without being controlled by a human, and eventually better quality of life for everybody. So I will explain very briefly about some of them, and then I will move forward with the examples. So eventually, it's all around sensing. So we have one side sensing, we have then processing, and doesn't matter whether it is formal or brain-inspired. So there is some kind of processing, and then operation and decision making. And all this should be energy-aware design, and this is eventually the framework of the research and motivation for the research that I have had during last 10 years. I'm covering the duration of the award only. And with the focus specifically in this talk with the application-specific IC design, integrated circuit design. However, it is not limited to the IC design. But I want to show that because it is very compatible now with the mission of the government of India for making actually from semiconductor side also India to move towards more independence from other countries. It's a strategic industry now. So, but one thing I want to tell everybody who may know, the process of our work exactly opposite to what Professor Ramanujan mentioned, right? Pronouncing correctly. In the domain of IC fabrication, it's a long process. And everybody has to be patient about that. Now let's see. First, you need to learn the basics. Then shape the circuit ideas for the problem to be solved. Then basic circuit design and analysis. And then step 4 is simulation. Step 5 is redesign if the simulations are not doing well because of the non-idealities and model is too complex to take care of them in the early steps. And therefore, go with the second round, which is redesign, and then simulation, and do the pre-layout validations. Then do the layout, and then do the post-layout plus package model simulation. Then redesign steps eventually again move back and start from the beginning if the really post-layout simulations fail, and you have missed something specifically in the early parts. Then if everything works well, then we convert it to an encrypted binary information, which is called GDS2 standard. See, it eventually means graphic data system. It's like IBM. Nobody knows what is the full form, but everybody says GDS2. Then send it over FTP, for example, to the foundry. And in the meantime, it is in Foundry, then do the design and fabrication of test boards, preparation of test setup, then receive the package or bare dies, silicon dies, or other technologies. Then do the test measurement and prototyping and demonstrate. A typical span is 2 to 4 years. This defines eventually lifespan of one MTech, one PhD, practically, with several MTech students. Therefore, here, if each one of them have gone through the same path, and that is, these are examples of some of the works which starts at the sensing level, and we always call them silicon-proven IPs. In this industry, IP means intellectual property, silicon-proven. That means it's a hard IP. It is already available and can be sold. And you may not believe that this is the base of that multi-billion-dollar industry, which is now moving to trillion-dollar industry, which is everywhere on your mobile phones, on this projector, on these laptops, in the controlling lights, everywhere. So here some examples that, and when we look at these works, these are based on the path I follow is energy aware, therefore voltage levels low, energy consumption sub-microwatt. And the job they do is, for example, converting analog levels to digital, which is very much required for the all processing which is being done today and is called now under computing category. And these are the kind of timelines I can tell you spent on each project. So for example, this is around 3 years timeline. Then, for example, a 50-fold range auto-calibrated sub-100 ppm resistive sensor measurement IC and system. This took us around 4 years, exactly the same thing that I told you. Or for example, a system which does the SpO2 measurement with a PPG IC with less than 2% error. This is almost same time span, and this was eventually a replacement with an industry IC available in industry to make it indigenous and low power compared to that. Then one of the first worldwide mid-radio band on-off key transmitter and receiver, which under a system prototype called BioVital. It also got almost same time span. And finally, 2 different eventually custom mixed signal CMOS parasitic insensitive capacitance to voltage converters, which is specific to soil moisture measurement with a range of frequency from 100 to 1.1. This almost took 5 years because there are 2 different designs. And finally, another work which is actually granted with patent and then very much has potential for the commercialization is time domain reflectometry system, which is one of the well-known techniques for soil measurement system, and these systems are expensive. This is not an IC work, but it's a system work, but because of its value, I added here. So I don't want to spend too much time on that. I just want to show you the way it goes. For example, I don't know how much you are familiar, but resistor and capacitor are simple elements, very simple elements. And you put them along with some other basic elements like a gain amplifier, a digital to analog converter, and make a simple circuit. What it does eventually, it will, here is eventually a technique which is called data sigma analog to digital conversion. And one of the things we follow is simplicity. Simplicity bring also low energy consumption. And that's why when it comes to implementation, everything is based on the novelty at the circuit design. How we put things together. And always, I mean, when we talk with the students, say that, see, look, if you can design a new circuit with your own and analyze it, you cannot be replaced with AI so easily. and that's the advantage. So this is the way I told you this process flow. So for example, here this is the schematic level, basic ideas, simulations, then we go with the layout, then this is the silicon die, and then put it on the PCB, and this is the whole process that I told you. And then characterize this based on the standard characterization. For example, the power spectral density based on frequency for a given excitation at a single tone frequency, and then get the sum of the specifications, which no need to go through details of them, but these are standard, eventually signal to noise ratios, and this is, say, typical maximum of 60 dB. So now imagine that this has been the whole kind of range of the outcomes for a PhD, which is around same topic. So which technology? This is actually SCL India. This is something which has been designed in India, fabricated in India, packaged in India, and tested in India. So this is one of the, and this first designs that we had all within India, and this was around 2017, 16 and 17 times, before even India semiconductor mission. And all these requirements with respect to power dissipation, you can see 590 nanowatt. Or for example, the effective energy consumption is 60 femtojoule, around 60 femtojoule per conversion. And these are figure of merits for any design in this domain. And here you see the flow, layout, silicon die, board, layout, silicon die, board. And after measurement results all in one. So this gives a glimpse and the publications, and listed also as popular papers in both the journals of the IEEE. And these are like a kind of one set of designs by actually one of my former PhD scholars, who is now a faculty in our own department. So he is Lakshmi Shah, and this was eventually the glimpse of his PhD work. So the second thing is another PhD work with this almost time span of 4 or 5 years, and starting from same simple concept. So eventually how we can have 100 ppm resolution in a completely auto-calibrated 50-fold range resistive sensor measurement. And there are many non-idealities. The technique uses the chopping techniques, which is very common. But here the idea we had and the novelty we have is that we are taking care of the parasitic capacitances by creating a two-frequency modulation with a new topology. And what you see in the gray color eventually is the design, which is on the chip, on the silicon, on chip blocks, and it's relatively very simple. Only switches, two current sources, which are AC current sources, one exclusive OR, which eventually creates a combination of slow clock and fast clock for double frequency switching, and the rest are on this board for the automatic calibration in 4 phases. This is also published in one of the, in fact, the topmost journal in the area of the IC design. And this is fully automated, and it is very small. So these are the kind of, I just wanted to show you the glimpse of that, how these devices are put on the silicon and how small they are. In fact, if you look at the whole design, it's occupied only the area which is shown between these red color blocks on the chip. And usually this typical area is not more than hundreds of micrometer by hundreds of micrometer. And then it is packaged, and then we can put it on a system. So now you see this system itself is a very small system. So the whole idea is about putting the novel ideas in this measurement method, which is completely ratiometric method. And as you can see, all non-idealities will get cancelled. And then finally, we will end up only a parameter which will give us the delta R by R from the measurement. And this was a completely automatic system. So as soon as you connect it to supply or connect it to the battery, it will start. And it has its own power management as well. And it will start doing the measurements. And these are the features of this work as compared to all worldwide reported works. which gives a wide range of the input, which is from 1 kilo ohm to 500 kilo ohm, adjustable current, and programmable for this range with 2 different sets of the currents, and with a very high rejection of the noise. So this was unique with respect to all reported works at that time, and it's available. So similarly, we had a METI funded project to actually develop the 2 solutions that I told you at the beginning. So with respect to SpO2 measurement IC and a med radio transmitter and receiver. And both projects, I give a full glimpse of the journey of the projects in one slide. So OxySense and BioVital, it took around 4 years. And it was by a group of 2 PhD scholars and around 10 MTech students. So this is the whole IC, which is does the SpO2 measurement, and this is the full system using the same IC and 2 transmitter and receiver ICs for med radio band. Med radio eventually is for the implantable and wearable devices, very short range, and it has a very dedicated band so that it can be also secure in this way. So, and these are the kind of, these are what we call chip macrograph, which is showing eventually the design of 3 circuits. And these are actually the Devarshi and Abhishek, the former, and Miraj, in fact 3 former PhD scholars. We actually took this, again, indigenous designs into the actual fabrication, prototyping, demonstration through fats, natural fat from animals, and then we took it further to hospital for further demonstrations. And this was quite the project with a lot of outcomes, with too many, in fact, journal and conference papers and granted patents. And finally, 2 different designs that I told you, and this was more about soil moisture measurement. We had a project dedicated to soil moisture measurement, and the ideas are simple. It's eventually switching a capacitor and converting that switching frequency depending on the sensor capacitor to a DC voltage, which can be easily measured. And this concept is not new, but we used it actually in a complete chip to make eventually a very simple, affordable soil moisture sensor with an indigenous IC tipping on it. Actually, the total area is not the area of the circuit, is only that small area which is shown over here, which is something around 300 by 300 micron. And this is just a simple PCB material, as simple as that. And then here, actually, we're just using something like a similar to an Arduino even controller. You can easily make a very reliable soil moisture sensor. And it has been also used and demonstrated with various types of soils. So these are some of the examples of actually measurements with the prototype, which is developed using IC. Volumetric water content is very important for agriculture, and these are the standard, for example, materials, glass beads and kaolin clay. And the 2 diagrams, one is using the, for example, here, glass beads, and one is using the reference that is similar to the same kaolin clay, but here this is our device, which is IC, which does it at 100 megahertz, and this is the moisture analyzer, a commercial device. So therefore, you see the difference between the difference between them, which has to be within plus minus 3% for agriculture applications, and here the difference was within plus minus 2%. This 2% is the same value, volumetric moisture content. Volumetric moisture content, VWC, is a very important parameter in agriculture irrigation. And this is what I wanted just to show you, and this was another project. So this was a PhD project, Surya, who is just submitted pre-synopsis. And this is with Mangesh, another PhD project. He actually made a complete And this is the second chip I Surya, which is this PLL, very recent. But this is actually a TDR system, which is completely prototyped by Mangesh, and this is actually has a lot of potential for being converted to the completely indigenized product, and it has been already demonstrated. And now we move to the computing. For computing, I'm not talking about neuromorphic engineering today because there is no time. I'm just giving one example, which is about frequency estimation and why computing specific to sensing is very important. This is a project that I had with a collaborator, Professor Ashwin Seshia, who is now actually a faculty member, professor in EE department, but at that time he was a professor in Cambridge. We had a joint project supported by DSC. So this is frequency estimation in a portable system with 0.1 ppm eventually effective error, RMS error, and which is the resolution of that measurement, with using 1 to 10 megahertz resonant MEMS frequency. So eventually the sensor is the MEMS. Method is gravimetric MEMS based ultra-fine measurement. What is that? Ultra-fine particulate measurement. This was eventually for the air pollution, and the focus was the fine particles which are less than 100 nanometer, and therefore looking at how the resonance frequency of a MEMS resonator is changing with the density of this and the amount of the deposition which is happening in a natural way on the MEMS resonator. And the variation of that frequency with that kind of resolution will give an estimate of the mass of these particles and therefore the pollution. This is much less than the range that optical techniques can manage. So this is just an idea to have an idea of this resonator plate, and this is the actual photo of the fabricated MEMS. But the problem is very simple. So if you have a resonator with, say, several modes, and say now we choose one mode, and let's say before our particle deposition, say frequency is 100 kilohertz, then it changes. So measure the new frequency. It looks simple. But actually here is the problem that you will see. The requirements for the accuracy is pretty tough. And give you an example. Suppose you have a signal combined with noise, which is very common in this case, and the frequency of resonance is 1 megahertz. And now suppose it changes by 1 hertz. So in 1 megahertz, the period of the signal is, period of the resonance frequency is 1 microsecond. If it changes by 1 hertz, that means that period of that resonance frequency has changed to 1 microsecond minus 10 picosecond. This is very tough to measure. Therefore, how to do that? We cannot measure it directly in a portable system. Therefore, we need to go with the techniques borrowed from communication systems and communication engineering. And one is frequency estimation. Can we estimate frequency very thoroughly? And this is where the computing and methods come to the picture. So therefore, eventually using a very moderate resolution ADC, low circuit complexity, low clock frequency, low power, transmit the data and do an algorithm which does the frequency estimation. So that was the whole novel idea behind these techniques. And then we moved to the mathematics and techniques for frequency estimation. For example, Kandan's method is one of the recently reported techniques. It's very interesting. These techniques are pretty new. And what we did is that we finally used 3 techniques, which was time domain and then frequency domain, Kandan and Jukanovic techniques. And these techniques actually appear to work well. And we made a system. Now the whole system made over this idea, and we called it Pro-FMS. So this is eventually MEMS-based particle mass measurement, which has the whole system. And this is the MEMS MEMS eventually sensor, which will resonate, and we made an oscillator around that. And this is the laptop, which eventually does any kind of frequency estimation from the sample data. So the details also we published in IEEE Transaction on Instrumentation and Measurement. And this is the actual simple portable system, and this is the MEMS. So this is pretty small. And we actually benchmark this small system with key site frequency, benchtop frequency measurement, which is one of the, which is expensive, pretty expensive compared to this board. And you know, if you are familiar, one of the ways of measuring the stability of a resonator is Allen deviation. And then by measuring this Allen deviation, we show that how this stable is this frequency, which eventually takes up to ppb, means part per billion, with respect to the stability of the oscillation. And then we made a mini kind of computer, later converted that small board to a mini computer to do everything on that and do it fast. And this was eventually an MTech project dissertation by Adarsh, who is now working in industry. And these are eventually features of the second version, which is based on a mini computer. And just this is one interesting thing to show you. So this is how do we eventually benchmark. So this is a G-length counter. And on the y-axis, you see the frequency. You can see the actual accuracy. And then we have two methods of Condon and Jukanovic. Now look at here. If you look at delta F by F in ppm, units, part per million. So this is the variation of a G-length counter, and this is actually our method, estimation method, which is even more stable compared to a commercially much more expensive benchtop system. But here there is a lot of computation and averaging which is happening, which allows to make the estimated frequency more stable, and then now related to actual deposition. You know, sometimes I think that what happens in our lungs. This is actually MEMS, initial MEMS, and you can see gradually it gets deposited by small dots. This is actually the carbon and silver. So initial measurement was with silver nanoparticles in the lab, which was actually done with the facilities available in the Cambridge. And here, of course, you see that it's completely covered. And the whole system was established in the lab to eventually do the benchmarking. Sorry. This is Pro-FMS small system sitting over here, and the whole arrangement around that to actually measure the variation of frequency with the deposition of the particles, which eventually was working very well. We again compared it with the commercial instruments, and the dark circles are showing the Pro-FMS, our system prototype results. So it shows that how frequency is changing as we deposit more and more over time, the nanoparticles. So now, having an idea of the sensing, having an idea of computing and trying to make everything small, we want also to make sure, and energy consumption low, we want also to look at how to actually make it even energy completely autonomous, in the sense that no energy from outside. The whole idea behind that is that because energy is freely available in the ambient, but there are many problems associated with that. So two of these works that I refer also are the PhD work of two eventually graduates, Mahima, who is now a faculty member in IIT Guwahati, and Gaurav, who is now working in Mediatek. So one thing I want to show you, one is about RF energy harvesting, and one is about both of them are about RF energy harvesting, but second one is also able to get other sources of energy. So one thing I want to show you is on the left side, which is one of the first experiments we did some time ago. So here you see something. This is actually Mumbai. And here you see the cell tower. antennas, and eventually tower with the antennas on them. Here you see a multimeter which measures the voltage, and here you see a kind of white sheet on which you see two of our circuits, and they are placed very simple on this sheet and then with tapes just to keep them. And these wires are taken out, and one of the people who was helping us, so he took it in front of cell towers, and this is almost 25 meters away from tower. So you have something in the air, you just take it, and you get 3.7 volt DC voltage. So you have a wireless supply. As simple as that, and it's so tiny and small. So that means that we don't need even battery. That means that we can think of even batteryless system. So therefore, this is why, because we are just 25 meters away from towers, and they are just distributing magnetic energy in a wireless manner all over the place, therefore, and it's available. Now, if you connect a load, for example, we connected 4.3 kilo ohm, still we can get more than 1 volt, close to 1.4 volt supply. And this is a typical, like, 0.4 milliwatt harvested power. And this is good enough for many applications. We are working, most of my research is around microwatt power dissipation, close to in milliwatts. So therefore, this is quite applicable, and many designs are now around these numbers. And then we converted this design to actually on the chip design. And then you see this is inside the blue part is only that circuit. The rest is other circuits. We put several projects on one chip because this is pretty expensive. It's just 1.5 mm by 1.5 mm and cost us around 4 to 5 lakhs. So we did the same experiment with the IC, and this is what you say. If you give it, for example, when you put mobile phone next to that, so we, of course, did the actual measurement, but we also reported it with mobile phone. In fact, demonstration with mobile phone to turn on an LED. So you just put the mobile phone close to this board will turn on an LED. But effectively, at 1 gigahertz, with a single stage rectifier at 2 dBm input power, it goes around 1.6 milliwatt harvested power, which is around 860 millivolt for 10 kilo ohm load. Similarly, for 5 stage and the reducing the input power, it gives around 0.5 milliwatt, which is input power. It gives, this is input power. It gives around 1 volt for a 1 mega ohm load. So this is the input power. So 2 dBm input power, 1.58 equivalent milliwatt. Just get some idea about while the eventually electromagnetic power, which is taken from ambient and then converted to the voltage. This is just to get some idea about what would be the levels. And the next work was actually to have same thing on the chip, but now eventually add the power management, a boost converter, and regulate the voltage. So this was the second PhD project. And similarly, it was demonstrated, but this is not using wireless. We actually give the RF power at 950 megahertz RF, from a 950 megahertz RF source. And this is a tiny design, 300 micrometer by almost 300 micrometer, which gives the solution. And you can see eventually, say, for example, 3 different demonstrations, measurement. For example, if you give minus 3 dBm, which is around 500 microwatt, the effective voltage, you get that the stage 1 is around 225 millivolt regulated at 1 volt. Similarly, at 0 dBm, 400 millivolt regulated at 1 volt, and minus 8 dBm regulated at 1 volt again. So it regulates at 1 volt independent of the input power, and that is what you want from a DC source. So it's like a DC source, but there is no plug-in point. So it's just taking the energy from the RF source. And this I showed you before. So what we did, eventually we removed the supply of this IC from Laxmisha. This is IC from Gaurav, and this was the Gaurav's project. So we put this energy harvesting system and the Laxmisha's IC here, and then we connected the VDD of Laxmisha's IC, which was 1 volt, to the output of the Gaurav's IC. And then we eventually, first, the only thing we have to do is to pre-charge the initial IC, and that's it, and then it will continue working. And we compare the one which is taken with a Ketley DC source and the one which is actually coming from energy harvesting. And chip was working similarly in the two cases. So eventually in 1 volt supply from energy harvesting with just 600 nanowatt power consumption. And comparison with the closest reported works at that time, so is listed here in this column. Only we need to pre-charge the capacitor, like you pre-charge a battery once and then you don't need to charge it again. So to conclude, eventually I try to give you a kind of journey of all these works, which are eventually summarized as the results of 4 or 5 years research in these 3 directions. And more is going on. But these are the actual contributors. So almost like till this point, these are all PhD scholars. And I have written where they are right now. And there are 4 MTech students. Number is more than that, but I try to at least keep those who have contributed significantly. And without them really would have not been possible, as well as collaborators. In fact, for example, Professor Dinesh Sharma from Electrical Engineering Department, Professor Ashwin Seshia, Professor Girish Kumar from EE Department, who is retired now, and all funding agencies, facilities in Electrical Engineering Department, and all funding from METI, DST. We also had DST, UKIRI, joint research that I mentioned. Different nano projects, one of them which got over last year, NETRO project, Europe practice for chip fabrication, and SCL within India for chip fabrication. This is extremely promising, and then now it's moving to the further. Colleagues also now are making in SCL. Many, in fact, chips are now actually fabricated in SCL. And this is just a glimpse of kind of different activities. This is the first kind of batch after COVID in-person graduation. So that's why it was also really, so red color are PhD scholars and blue are MTech students. So this is one of our labs. These are the kind of get-together before COVID. This is before COVID. So COVID has become a kind of history event. So, and then some of the visits, for example, by various authorities, various scientists and government, and demonstration of some of our prototypes. And then also this is another lab. This is integrated systems lab, embedded systems lab. And all this are happening in the lab. And then we have also 2 startups, and the 3rd startup, we are also working on it out of all these activities. Thank you.